So you've heard about it. All right. It won't be a quiz today. We'll make it our last lesson of the week, whenever that is. When's our last lesson of the week? Is it Wednesday or Thursday or Tuesday? Wednesday. Okay, so that sound good? Now, the way these quizzes work is they're like, 10 multi-choice questions, maybe a couple of short answers. I mean, and it'll be on D2L. Yeah, I'll tell you the rest of the rules. I think you might be allowed to have a cheat sheet. And okay, so when we have the tests, you can't have anything like that. When we have tests, you can't have cheat sheets or anything like that. We use Lockdown Browser. But I'll just check. But yeah, I think that you can have a cheat sheet. So let's talk about computational thinking. Not this chapter. Yes, very good. It's about the first two chapters, but not this chapter. That's my understanding. Okay. So all that stuff we talked about first. Sound good? Computational thinking, it doesn't mean thinking like a computer, but if you have done computer science training, then the things that you learned in computer science would help you to do computational thinking. However, you don't have to do computing to do computational thinking. And the theory behind this lesson is that everybody should learn how to do computational thinking. It's good for doctors, lawyers, HR specialists. It's good for everybody, right? This is a type of thinking which is problem solving. You can do computational thinking without working on a computer. However, if you were a computer scientist and you went through the process of designing software, designing hardware, you probably would have been doing some computational thinking, and that would be very useful to you. It'd be a skill that you could carry over to some other area. So as it says, computational thinking allows us to take a complex problem, understand what the problem is, develop possible solutions. Now notice solutions, not solutions. So the idea is that we come up with multiple solutions, and then we present these solutions in a way that a computer could be used to help solve them. Now, it wouldn't have to be solved by a computer, but if we could present them in a way. So when we use a computer to solve problems, there's a very sort of limited way that we can do that, right? We have syntax in computer problems and things like that. I mean, it's in computer programming language solutions. We have syntax. And so we have to structure the way we problem solve very, very carefully. And that's a good thing to learn how to do, even if you're not going to be a programmer. That's the idea of this lecture. So computational thinking is an idea that has sort of caught on in computer science groups more in the last sort of 15 years. We'll talk about a presentation that was made, and it became a journal article by Jeanette Wang, and she sort of described in her own words what she thought computational thinking was. That was actually at a conference that was entitled Computational Thinking. So people are starting to talk about this and think about it. What is computational thinking? What are the benefits of computational thinking? Who should be doing computational thinking, and how do we do it? And so the other thing I should mention is in this class, we haven't assigned you a textbook. However, there is a book which is mentioned as a good sort of reference that you could use as a textbook, and it's called Problem Solving and Computational Thinking, as far as I remember. And it's by, I think, Beecham. And I did give if you look back through the PowerPoints, I did give a reference for that. Well, let's just see, because I see people grabbing for things to say, oh, where's this book, right? So Beecham, I think it's Beecham. Yeah. Computational Thinking. I think it's Beecham. I probably spelled that wrong. It's got when I go to Beecham, it wants bechamel sauce. It wants to do what do you call it? Lasagna. Let's see if I got that right. I think it's Beecham. Beckham, not Beecher. Beecher, is it? Do you see it there? Where? Carl Beecher. Thank you. So did I give you that, or you just found it yourself? All right. There we go. Carl Beecher, that's it. Computational Thinking PDF. Oh, it's on a PDF. Oh, there you go. That solves some people's problems. No, it's not. That's just an article about it. All right, so you would probably, no, not that, not the PDF. So you'd want it on Amazon or something. Now, I actually have a, there we go, Beginner's Guide to Problem Solving. That's the one, pretty sure. Yeah, that's the one. So you could use that. It's going to cost you money. Or you could go to, I use Scribd, SCRIBD, and they give you online access to it. You can see all of the words, you can see all the images, and it will work as an audiobook. You can listen to it, so you can sort of just listen to a chapter at a time. There's like 4 or 5 chapters in there that are pretty good, that directly relate to this course. It's not the whole book, but there's 4 or 5 chapters on it that are pretty good. So yeah, I recommend that. Enough said on that. But so he talks about computational thinking a bit. Right, so it is a topic that's people are thought about and put into words what they thought. These 4 components, let's call them, if we were to look at computational thinking and say, well, what is it made of? What is it composed of? These are the things that it's composed of. And actually, when we say these are the things it's composed of, you can think of these as steps also in computational thinking. We could do these one at a time. So that is, we would start off with decomposition, and then we could do pattern recognition, and then abstraction, and then lastly, algorithms. So decomposition, you have a big problem. It's too big. We break it into smaller problems and repeat. We keep doing that until we get the problems small enough that we can actually attend to them and solve them. So that's represented by this diagram. You see the big problem broken into smaller problems, again, broken into smaller problems. And eventually we get these ones down the bottom there that are our size of problem that we can solve, and we solve them one at a time, put the thing back together. This is not a new idea, and it's, I mentioned that they had this conference about computational thinking in like 2006. This idea of breaking down problems into smaller bits, that's been around for before I started computing, right? I mean, we used to call it stepwise refinement. You break it down and yeah, okay, anyways. And you get modules that are small enough that you can build that into a computer module. And the thing is, there's so many things that you have to do with a computer module when you write it. You have to design it, then you have to write it, then you have to test it. And it's just a lot easier with smaller code. And so that's what we tend to do. Pattern recognition, that's the next step, we would say, in computational thinking. The idea there is, oh, did I ever do this before? Or has anybody else done anything like this before? Is there something, that I can relate to? Maybe I've got a solution which is 95% there that I could customize or something like that. So pattern recognition, where we recognize that we've done this kind of thing before, we don't have to reinvent the wheel kind of thing, right? So we can use something that we've got before in our back pocket. Abstraction is been used by human beings since, I don't know, 30,000 years ago or something like that. You go to the caves in south of France. The people who were living there, by the way, were just like us, except 35,000 years ago. They drew on the walls. All right. And the funny thing is, they drew on the walls animals, but they weren't like portraits of animals. You know what I mean? They were abstract. You know what I mean? They were almost stick figure animals. They're quite good. Nice, how you say, color and sort of composition to them, but that's abstraction. We do that a lot in art. We make something simpler. It takes a complex something and make it something simpler. I'll give you another example of abstraction. You're sitting with your friends, in a social event, and somebody says, I'll bring something to you to your house, whatever they're going to bring to you. Oh, I don't know how to get there. Oh, let me just draw you a quick map. And so you get out a pen and you draw this street, that street, and then you put a little block there, X, that's my house, right? So it doesn't actually, you got a piece of paper. It doesn't look like your street, but it's abstract. They can follow it. You know what I mean? We've got it as simple as we can. We've removed all the information that we don't need. And that's represented by this diagram here, where we have something complex and we represent it by something simple. And that's just how people are, right? We're doing that all the time. We're always trying to represent something complex by something simple. And in fact, it's quite an important skill in just being a successful human being. The next thing down there is shows a diagram which relates to the last step, which is the algorithm. Once we have decomposed it into small bits, looked and see if we can sort of reuse stuff. We've abstracted it to get down to the simplest, and then we can, the next step after abstraction, and abstraction leads right to it, is some kind of description of the problem, of the solution in a thing called an algorithm. So an algorithm is going to be step-by-step way that we actually solve this. And so one of the ways that it could be would be a diagram like this, because the diagram has very meaningful symbols. Each of those symbols there has a different meaning. And so by looking at that and having it labeled, you're skilled, don't have to be skilled, really, you know, it's almost intuitive. You can teach people how to use these flowcharts quite quickly. But so somebody who's spent 20 minutes learning how to do flowcharts will be able to look at these flowcharts and know how to solve that problem. So that's really quite good. Okay, so this is the thing about decomposition. So we're going through those steps one at a time, or those components. The first step there is about decomposition. Because our problem is too big, so we need to break it into smaller bits, and then we have then we can address each of those pattern recognition, because maybe we've already solved something like this problem before. Abstraction, because we get rid of everything except the most important details. We just focus on the most important. We put the rest aside. And then lastly, we put simple steps together, and that's an algorithm. Now, an algorithm is not going to be a computer program. An algorithm is just instructions how to do it. You go from the algorithm to the computer program. Somebody will look at the algorithm. It might usually the same person who wrote the algorithm will look at the algorithm and then put that into computer code as a solution. Okay, so I promised you at the start of this lesson, or I told you that at the start of this lesson that you don't need to be a computing person to do computational thinking. But so far, I've just been talking about examples in computing, but it does apply to other people. Hello. And that's the point here. Thinking computationally is not the same as programming. It's not the same as coding, because coding could just be taking that abstract algorithm and putting it into computer code. You know, I mean, it doesn't involve the whole problem-solving process. It's just abstract to code. Right? It's only a little part. It's only one step out of the 4 steps. Computational thinking then is broader than computer programming, and actually can be done by people who are not computer programming. So let's have a look at an example. So say you decide that you want to meet with your friends at a particular place. Then you have some decisions to make about how you go about that, right? So, I mean, you could just go onto Google Earth, not Google Earth, sorry, Google Map, or Waze, or whatever sort of mapping tool you've got. And you could just say, get me the fastest way there, get me the shortest way there, get me the one that uses the least amount of gasoline there, get me the one that doesn't go over any speed bumps, you know, get me whatever is important to you in how you solve that particular problem. You could use that as a way of measuring which of the possible routes are available would be best for you. And once you've done that, then you get your step-by-step instructions on how to get there. You know, turn left here, turn right there, that kind of thing. And that can be done by Waze or by Google Maps, but you have to decide which one you're going to do, right? So the deciding and the planning that you do, that's computational thinking. The actual step-by-step in the map that Google Maps does, that's not computational thinking. That's just step-by-step stuff. It's part of it. It's like programming, right? So we got another example. Then you want to meet with your friends for a social activity, but you haven't got as far as deciding where it's going to be or what you're going to do. You just know you want to hang out with your friends. So you've been put in charge for some reason. And so because you're put in charge, you have to make the final decision, where we're going to go, what we're going to do, are we going to eat, all of those things, right? So you've got that. then you would sort of perhaps do some data gathering by surveying your friends on what their preferences were. Perhaps, I don't know, unless you just decide, you know, my way or the highway, we're just going to go and do my thing. But the problem with that is that maybe not everybody will come. And if they come, maybe they won't stay because they don't like it. You know what I mean? So we probably want to find things that people want to do and that they can afford to do, that they have time for, and it's in a place where they can meet, etc. So what kind of questions might you ask? Well, here it says, consider the time, money, weather, and friends' interests. So you might ask them, in the interest of time, I'm just going to go quickly. Is that all right? You could ask them where, you know, do we want to meet at Katara? Do we want to meet at, you know, Doha Sports Club? Or, you know, do we want to meet at Costa Coffee? You know, what kind of thing, what kind of ambience do we want? Do you want to eat? Do you want to just, maybe you want to watch a sports, you know, so somebody's got a big TV so he can watch the World Cup or whatever. So here's some things that actually have come up in things we've already mentioned, right? So you might reflect back on, oh, you know what? A couple of weeks ago, you know, we went down and we went to that coffee shop, and you know, they had good food and everybody enjoyed themselves and it wasn't too expensive and there was enough room. Maybe we can do that again. You know what I mean? So that is sort of repeating something that works. Doesn't that sound familiar from the previous slides that we talked about, right? So, you know, can we repeat something that works? Then you, of course, how much money, what will be the weather? The weather's too hot and humid. You might want to be inside rather than sitting outside somewhere. Thinking computationally, I don't know if you guys, so this is like 1980s computer program, right? Our computer game. I don't know, do they still have anything like this? When I was in the 1990s, they had this thing called Duke Nukem. And yeah, he used to bounce around and he had these tools that he would shoot. Yeah, it looked kind of like that. All right, so it looks to me like your goal is to get to the exit. But I don't think you're going to get to the exit unless you have that key. Agree? And it looks like maybe you have, man, how do you get from here to there? Maybe you just walk up the stairs. And then you have these barriers, which have been defined as enemies. So I suspect that enemies, because they got a death head symbol, that maybe they could stop you. Worse than stop you, right? Like make you leave the game. So you probably have to have some way of dealing with them, right? So what are the questions you would ask yourself? If I was going to play this game, well, I know how people play. They just do it until they learn, right? Or they ask somebody, what's the cheats? What's the cheats on this game, right? And so, you know, so you'd find out, oh, you know, if you do this code, then you can blow up those death heads, you know, or if you do other things, right? How do we go up? How do we go sideways? How do we pick up the item? How do we turn it to open the, you get the idea, right? So what are the questions they'd ask? What items do I have to collect? That'd be right. How do I collect them? Yeah, how do you get that key into your hand? How long? So you can see that at the top there. Yeah, you'd look up there, right? Because up the top there, it says something about 70 seconds, it looks like. And where's the exit? How do we get there? Get the idea? And we got some, I think the death heads must be the enemy. And so that enemy would probably be fighting back. So there we have listed here a way for us to learn a little bit more about the 4 different elements or components of computational thinking. And so this is color coded. So if you start there on the left with the blue, we've got, we want to fill in all of these boxes. Now, actually, I can't sort of move them, so we just have to find from here. What would be an explanation of decomposition? So we're gonna explain each of these 4 things in the blue. Breaking down complex problem. There we go. So we got that. We got our first. What would be an explanation of pattern recognition? Looking for similarities. Perfect. So far, 2 out of 2. What would be an explanation of abstraction? Focusing on one, is that what you said? Yeah, and so by process of elimination, which is a logical way of thinking, process of elimination, we know that the last thing there, algorithm, must be step by step. Yeah, and as soon as you see step by step, you know that that's an algorithm. Yeah, step by step to the solution. So we got the blue stuff. Meeting up with friends. So can we say which part of these is a decomposition for meeting up with friends? Yeah, I'm not going with the, I'm not feeling with the last one. And yeah. Because the last one is step by step. So I'm thinking the last one there is going to be algorithm. What'd you say? That's what I'm feeling too. Options of where to go. And then, so I put that there. What have you, oh yeah, that's got to be, what's this? What have you done previously? Pattern recognition. We did talk about that. Transport, that would be abstraction. And the last one would be step by step. So now we're down to the orange one. I think they're actually sort of in order from left to right, right? Left to right becomes top to bottom. So decomposition, creating a computer game, explanation of how to complete the level. Would that be? Oh, no, that's not. We have to have, I think this would be the start, wouldn't it? Ways. Yeah, so we come up with multiple ways. That would be our decomposition. Pattern recognition, have you ever done this before? There we go, similar. So it actually starts here, 1, 2, explanation of how to get to the complete level. That would be the last thing. Location of the exit would be the abstraction. So let's see. Yeah, there we go. I was wrong. Look at that. I got these two in the wrong order, according to this. Ways of getting, so if you had it in this order, pat yourself on the back. Can't win them all, right? Anyways, I think we got the idea. Yeah, so let's look at decomposition. You're going to do word problems a lot. Solve all kinds of something, developing a something. All right, so one of the problems that it references is the COVID problem. You know why I'm holding up my mobile phone? Because on my mobile phone is an app called Etheres. And Etheres was developed apparently as a solution to the COVID problem. We have multiple solutions to the COVID problem. One of them is some of you guys are wearing face masks right now. That's one of the solutions. Another solution was a vaccine. Wow, wasn't that nice? And another solution was stay home and do Zoom. And another solution was, well, let's know what is your health status at the moment. And so we can do that with Etheres, and it has Bluetooth on it, and you can't really run your Etheres without the Bluetooth. And so the Bluetooth is communicating with everybody else's phone who's near you. And so if somebody comes near you and they're red, then you're going to get a message or something. Maybe you'll get a message from the Department of Health or whatever, MOPH. Will say, go home and stay there until you've had a rapid antigen test, right? Okay, so got another problem here. What's this one? Computer carry out. Blah, blah, blah. So when you're faced with a complex task, step by step, it's going to be part of it. It's kind of good to know where to start with that. When I think of step by step in furniture, I think of IKEA. IKEA is really good at doing step by step furniture, and they give good instructions. The instructions come as a piece of paper with many pages sometimes. Sometimes they have 30, 40 pages because they don't have any written instructions. If you look at it, it's nothing written. That's because IKEA, I think, this is what I think. I think IKEA, they're from Sweden. Sweden's a small country, and but they sell their stuff all around the world. And so how many languages are you going to write this in, right? I mean, who knows Swedish? Hardly anybody, right? Only Swedes know Swedish. And so they put it in pictorial. But the other thing that IKEA does is they put all of those instructions onto their website. So all you need to know is the name of the product that you bought, and each product has some weird Swedish name, right? Oh yeah. I mean, they just mean nothing, do they? You look at it as like Borgvåg or something, what is it? And so you look it up and you can find your instructions online. I think it's kind of cool. So they thought this through. They did computational thinking, and they came up with, I would say that the instructions that IKEA has, those are an algorithm. They give you the raw material, and they give you an algorithm how to make your furniture. And that algorithm is very abstract, right? Those nice pictures without any words. There you go, computational thinking with furniture. So the other point here is about computational thinking and computer programming and everything associated with computational thinking and computing. There is a creativity involved, meaning that there's no one way to solve any particular problem. Usually there's multiple ways. And so our very skilled individuals, they'll come up with something maybe a bit more efficient. Somebody else may solve the problem, but maybe not quite as elegantly. There's a creative process in there. So what I mean by that also is you should be aware as students in a college, if you're going to be writing computer code of any kind, that instructors know this. It's creative. You have to create your own structure for your program. It should be different than what other people do, because nobody thinks the same, right? I mean, if you get five programs handed in for the same assignment and they all look the same, you know what happened, right? There's no way 5 people came up with 5 different programs for that. You know what I mean? At the very least, they're going to have different variable names, and probably the structure will vary as well. So that creative, that's kind of nice. I think the creative bit about it, that keeps computational thinking within the human realm, because creativity is not the strong point of computers. Computers are good at repeating stuff, but they're not really good at, oh, here's a cool idea that nobody else ever thought of. I'm going to try it like this. They're not really that good at that. Humans, on the other hand, yeah, we do that all the time. Like every day, every time, right? When you're talking to your friends, you're saying different stuff, you know, than anybody else ever said before, for sure, right? And you're doing different stuff. And that's cool. Okay, so this guy, Hoya, he was, I guess he's Hungarian, yeah, so Eastern European. So he said, well, you know, maybe we can learn something from some other sciences. Computer science is a science. What do scientists do? Maybe we can apply that to what we do. And yeah, so he came up with this. We had the scientific method. This has been around since the Enlightenment. So that's like 500 years. And so the idea is, before that, I need to pay proper respect, particularly to our Arabic students, because Arabic people back more than 1,000 years ago were using scientific method, and Aristotle was using the scientific method before that. So 2,000 years ago. In Europe, they weren't really using the scientific method until about 500 years ago. But yeah, in Egypt, Baghdad, they're using the scientific method 1,000 years ago. Anyway, so what do? We form a hypothesis, we plan an experiment, we execute the experiment, and we evaluate the results. Now, the scientific method requires that hypothesis, we try to prove it wrong. That's what we're trying to do. So that's why we have peer-reviewed articles, etc., is because we put our hypothesis, we put our experimental results, we publish it, and then other people will look at it and they will try and repeat it. Can we get the same result that he got or she got? And if we don't, then, you know, we might say, well, your idea was good. However, we found out that this particular experiment negates your conclusions, that your conclusions need to be adapted, updated. And so we try and do that first. So we have our idea, we do our experiment, and we try to prove our idea is wrong. That's the idea of the hypothesis. And if we can't, and we've designed all these experiments and we think that, well, you know what, everything I do, I can't prove this wrong. So I think it's right. So now I'm going to publish it. And so that's the experiments and evaluating the results. Now, Polya said, well, we can do this in computing. We can adapt that. So forming a hypothesis, that's kind of like understanding a problem. We're not actually doing experiments here. What we're doing instead is we're making computer systems. But we can't do that without understanding a problem. That's kind of like forming a hypothesis. Planning an experiment is kind of like devising a plan. Yeah, plan. Executing the plan. Those things are the same, right? And then review and extend. I guess you could say that sort of creating computer systems is kind of like the scientific method, in that you're saying, what the testing the hypothesis is, will this computer system do what I think it will? I think that my hypothesis is, I think this computer system will do this. Okay, now my experiment is, I'm going to go and build this computer system. And then I test it, and oh, it did or it didn't. And if it didn't, well, we update it or we get a new one. All right. So as it says there, when we see a big problem, if you just look at the big problem, you could be sort of put off with it. You could be, it would maybe scare you. Then the correct way to approach that is to break it into smaller pieces. What's the old saying? 1,000-mile journey starts with one single step. And so that's what we do. We take one step. And the first step is trying to understand the problem, trying to understand and find the problem. Do not start trying to solve the problem until you've spent enough time on that first phase, which is trying to understand it. You must spend it, you must put in the effort of understanding the problem. Otherwise, as you start developing the solution and you've sort of got a half-baked idea of what you think the problem is, and that you'll end up sort of solving the wrong problem, or yeah, and that could be bad for you in terms of time and energy. So that's why do spend a bit of time on that. So here we've used the word starting point, representing where you are when you see the problem, and then the goal being where you'll be when the problem has been solved. So so we look at it in that terms, and that's the way humans are. Not just humans, even animals are in a way. I mean, what it is we are goal oriented, and actually, you know, there's a psychologist who has a lot of stuff on YouTube that I listen to sometimes. Nice guy, but he sort of says that if you want to be happy, he noticed that happiness happens when a person is making progress towards a goal. You know, when you're making progress towards a goal, you seem to be happy. When something frustrates you in that goal, then you tend to not be so happy, right? And so the thing is to sort of get your goals right and then sort of make progress towards it. Now, you could also learn a bit of Stoicism, which would be that what Stoics do is they try and moderate their emotions, so that even when they don't meet their goals, they're happy. But the thing is, and that actually helps them to move towards the goal. So let me tell you what I mean by moving toward a goal. If the simplest goal would be, I have a problem. My problem is I'm hungry. That's the simplest problem, right? Okay, so how do I solve that problem? Well, I move myself to somewhere where there's some food, or I move some food to me, and immediately I'll be a bit happier. Now, we all have this sort of goal-oriented thing when we get in a car and start driving, right? You're driving, and then if somebody cuts you off, and you get set at the lights. Yeah, unless you're a Stoic person, and maybe you are. You know what I mean by a Stoic person? A person who's totally in control of their emotions. Unless you've told yourself, and I try and do this when I get in a car and drive, because I know that, you know, I don't want to be emotional in the car. It's dangerous. So, you know, what I'm going to do is, I don't care how long it takes me. I'm just going to enjoy the ride. Whatever people do, they do. I'm just going to avoid them, and you know, and then I'll relax and I'll be happy. But if you're not like that, you know, somebody cuts you off, they break in front of you, you get right, or you're sitting in the line outside Starbucks, right? You know what I mean? That's a big line, and you're motivated, right? I want that Starbucks, and you know, somebody cuts in front of you, right? How do you feel? You get the idea. You get what I'm saying. So really, that's just goal orientation and progress toward the goal. That person cutting in front of you, they're not hurting you, but you perceive it as, you know what? I'm further away from my goal. All right. The opposite happens. You arrive at Starbucks, and the guy at the front of the line says, hey, you know, I don't need to go in here. You come and take my place. How do you feel? It's like, oh man, I'm getting toward my goal faster than I feel good. All right, so yeah, that's how we are. We're goal-oriented, and we do that with our programming, we hope, or our problem solving. So the thing is, we have to understand, what is my problem? What is my problem? And I don't mean it in that smart alecky way, you know, that people say, you know, what's your problem? What is my problem? What is it that I need at this point? Well, what I need is a faster computer system, because my customers are going away, because the accounts is not working for them, this kind of thing, you know. What I need is whatever, and it'll be some kind of business problem. And because, yeah, you want to make more money or whatever. So, as I said there, and this is kind of repeating stuff I said a bit ago, you need to understand the problem. Somebody gives you a problem. They've stated the problem in their words. Don't just take that. Take it and restate it in your own words. By doing that, you have to understand it, right? If you take one way of saying something and put it into another way of saying something, the process has to go through you understanding it. And actually that's a good learning technique, is to take something and restate it in your own words. And when you've done that, then you'll understand it better. Now, the next point there is with the abstraction. Can we represent the problem with stick figures or some other representative diagram? If we're doing that, we're removing the non-important things, and it's also proving our understanding. Now, the point about the bottom there, there's knowns and unknowns at the start. You need to be prepared to update your understanding of the problem as you go. Okay, whatever the problem, details, design, blah, 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 too early. Making the point again is that you need to make sure that you spend the time, do the work to make sure you've understood the problem before you sort of rush in and try and starve it. We've got an example on the next slide. All right. So this one, you've been put in charge of organizing a conference, and the conference is going to be one of those. It's going to be a conference that people who are, successful people in a particular industry. Let's say it's in the computing industry. Successful people would be attracted to it. So, okay, these people are all earning more than $100,000 a year. They're used to eating well. They're used to meeting with other people of their similar understanding. That's the kind of thing that I want. Right. So I'm probably going to, cater with like 5-star hotel food. I'm going to try and attract big names, not people that are unknown, somebody that people have read about, that's doing something interesting. These are the type of people I want to come to. I want to headline my conference. And then, of course, I'll attract a lot more other people. Right. So there's a few things that we would need to do in this conference. We need to find out, we have to decide who we're going to invite. We have to decide what is going to be the topic. We have to decide what are we going to feed them. We have to decide where they're going to sit. We have to decide what's the venue. All right. Now, some of those things we need to start on straight away, because, it's like water flowing downhill, right? We can't do the things at the bottom until we've done these things at the top, right? So that's what this exercise is, right? Which are the things that are the more important that we have to look at now, and which things can we postpone and do nearer to the time? So let's have a look. Dinner or light snack. Do we decide that now? Is that part of our goal definition, or is it something that we can do later? Yeah, very good. I would say that that's not now. We can do that later, because, after we've determined everything else. How many chairs for the audience? I'm thinking that later. It depends on how many people you're going to have, right? It depends on where you're going to be. So those other things have to be decided first. Topic of the conference. That's goal definition. I mean, this is the big one, right? This one we have to decide before anything else we look at. That's the big one. Seat chart for the guest speakers. All right, I didn't make this. All right, so you could argue with the person that made it, but okay, think of it this way. Supposing we came up with 2 different seating charts, and one, I've got this guy sitting here, and one I've got him sitting there, right? How much, you see what I mean? Is it going to affect the conference that much? Maybe a little bit, depending on exactly who it is. But as I said, depending on exactly who it is, depending on who we've got there. Which company will do the advertisement? I'm thinking you could do that kind of at the last moment. I don't know, at the last moment for advertising. Not at the last moment, because you want to advertise months in advance. But, possible list of guest speakers. Yeah, That's going to affect all these other things, right? Who we got coming? What's our topic? That's going to affect everything. So our goal is going to be the topic and who we're going to have. And then after that, these are sort of procedural things. This is going to be the thing that we really want. So whatever. Better defining a problem goals, write them down. Goal not written is only a wish. I don't know if you ever heard that before, but yeah, we need to write things down and sort of also written down and then I wanted to use the word disseminate, but there's probably a better word for it. Yeah, we need to get it to everybody who's going to be involved. They have to have written down exactly what this goal is. All right, here's a problem. This problem helps us to understand better decomposition. So what we have here is we have a policeman who is the problem solver. And then we have a problem. It appears that the problem is that there was a smash and grab robbery. Call that a robbery? Or a burglary. I think a robbery is when there's violence on a person, right? So I don't know, maybe there wasn't a robbery. So a smash and grab, somebody saw it. And it happened at a particular time. And somebody else has been doing stuff like that before. And they left some footprints. So what would the police officer be looking at there? Yeah, absolutely going to look at evidence. Yeah. So there you go. They're going to look at evidence. Where's evidence? There it is. What evidence? They're going to look at that. They're going to look at, you know, what exactly was that crime? Time, witness, and the similarity. Doesn't that sound like the stuff we talked about too, right? So he's not, he, not using a computer, right? But doing computational thinking, just the way that we have been describing it. Here's another one for you. All right. So can you do some computational thinking? You are making a sandwich. Now, let's say this is a sandwich for somebody you care about. It's not just that you're hungry and you don't care. You know, so you just get slap it together, right? Well, some of you actually care about it anyway. So yeah, you care about this. So what would you do? What kind of questions would you ask? I'll give you a hint. If you went to Subway, they ask you questions. What questions do they ask? What kind of bread? Yeah, all right, because you got 4 different kinds of bread, right? What kind of bread? Yeah, what are your fillers? And do the meat? Yeah, which meat kind do you want? Yeah, you know, do you want butter or do you want mayonnaise or both? Yeah, so I mean, you know, yeah, there you go. So asking those questions is going to help you define the problem, right? So as I said, if you're at Subway, you're giving this guy a sandwich. The problem is that guy's hungry. He's goal-oriented. Goal-oriented. He's gonna want a sandwich. He's going to want a particular type of sandwich, right? So if we don't get this problem defined right, we're going to give him the wrong sandwich. He's not going to be happy, right? And if he's not happy, that could be, I don't know, we lose customers, something like that. Okay. So I am done talking about that. We got 2 hours. I spent 40 minutes talking, and you guys, credit to you. That's awesome. What I think is,